In this video, I'm going to talk about the Crawford-Sobel model. We'll talk about its equilibrium and also the welfare properties. So let me recall what we have studied in the previous lecture. I showed you two equilibria of the Crawford-Sobel model. One is the very simple babbling equilibrium, where no meaningful information is conveyed. But I also showed you a binary message equilibrium, where the range of possible values of theta, the state of the world, is broken up into two categories or two intervals, divided by some threshold. And we showed that unless the bias is bigger than 1/4, this binary message equilibrium exists and can be constructed. So what in general are the kinds of equilibria you find in the Crawford-Sobel model? The answer to that is all the equilibria are partitional equilibria, meaning the whole range of possible thetas, which is the interval 0 to 1, is broken up into a number of sub-intervals. It's a finite number of sub-intervals. And corresponding to each sub-interval, there's a distinct message. So basically, the listener or the receiver gets to know which interval theta lies in, but within the interval, there's no further information which it becomes available. So let's study the general equilibria of this model. So here's the description. General partition equilibrium of the Crawford-Sobel model. So the range of possible thetas is broken up into these intervals, right? So here we are looking at a partition with n intervals, not just two, some general n. And so let me draw a picture to make it clear. So the range of possible values of theta lie between 0 and 1. And we are trying to construct a partition equilibrium with n intervals. So there's going to be a number of cutoff points and so on. And there will be one in the end. And the cutoff points, let's call them theta 1, theta 2, theta 3, so on, up to theta n minus 1. And then the endpoints 0 and 1, let us label them theta 0 and theta n respectively. Okay, so the messages will take, in equilibrium, there will be n distinct messages. So if theta falls in this leftmost interval, there will be a message m1. If it falls in the next interval, there will be a message m2, m3, and so on. And for the last interval, the message will be mn. Okay? So can we construct an equilibrium of this sort for some general n? So let's try to do it. Suppose this is accurately describing the message strategy of the sender, of the speaker. Now let's think of the receiver's best response. So the receiver thinks that this is the message strategy of the sender. In equilibrium, players correctly anticipate the strategies of others, so following that logic. So when the receiver hears the message m1, the receiver knows that theta is lying in this interval, and we are dealing with uniform distributions, so the updated belief will be theta is uniformly distributed in this first interval. And so the optimal action choice will be the expected value of theta, the conditional expectation. And that is, as you know, for uniform distribution, the expectation is the midpoint of the relevant interval. So this is the midpoint. And that is going to be the action choice. So when message M1 is heard, this first interval is the relevant one. Its midpoint is the action that will be chosen. Similarly, if the second message is heard, then the receiver knows that it lies in the second interval, so he chooses the midpoint of the second interval as his action. That's A2. Similarly, there will be some A3. So for each interval, if the corresponding message is sent, the midpoint of that interval gets chosen by the receiver, the decision maker. All right? So if you're talking of the kth interval, remember that means the kth interval is, so if message mk is heard, that means that theta lies in the interval theta k minus 1 to theta k. And that means that the action chosen after the message is ak equal to midpoint of this interval, which is half of theta k minus 1 plus theta k. Okay, now the question is, there are two questions. One is, when can we construct an equilibrium of this sort with n intervals? What conditions are needed? And you will see that we need a condition on the bias not being too large. Secondly, what do these values have to be? These cutoff points, theta 1, theta 2, theta 3, can we solve for their values applying equilibrium logic? So let me show you how that is done. So let's focus on two adjacent intervals. So here's theta k. Here's theta k plus 1. And here's theta k minus 1. Okay? And as you saw with the binary message equilibrium, the critical condition is the indifference condition. So when theta falls in, or when theta is exactly equal to theta k, what message should the sender send out? So remember that if he sends the message mk, then the action chosen will be ak. And if he sends the message mk plus 1, then the action chosen will be ak plus 1. Okay? So, for this to work as an equilibrium, whenever theta is drawn from this interval, the sender should have an incentive to send the message mk, not any other message, which implies that he shouldn't prefer the message mk and therefore the action ak. He should prefer that action to other possible actions, including ak plus 1, right? So people, when theta is in this range, the sender prefers ak to ak plus 1. On the other hand, if theta is in this higher range, then he's supposed to prefer the action ak plus 1 to the action ak, which means at the cutoff point, he should be indifferent between these two actions, which is to say, he should be indifferent between sending the message mk and the message mk plus 1. And this indifference property is what we're going to exploit to solve for the equilibrium, right? So what does indifference mean? At theta equal to theta k, then the sender is indifferent between the two adjacent messages, and therefore the two adjacent actions, which is ak and ak plus 1. Okay? Now, if theta is equal to theta k, then what is the sender's bliss point? What is the ideal action of the sender? Well, that is theta k plus b. Remember, b is the bias factor of the sender. Sender always wants the state plus some constant b to be the best action. So if the sender is going to be indifferent between these two actions, that means that the sender's bliss point, namely theta k plus b, should be equidistant from the two actions ak and ak plus 1, right? And that captures the indifference condition. So that means theta k plus b minus the lower of the two actions, ak, should be equal to ak plus 1, the higher of the two actions, minus theta k minus b. So this is the critical condition. This is our indifferent condition, which should hold at every cutoff point. At every cutoff point. Yes? And provided if we can find a set of cutoffs where each of them has this property, then we have successfully found an equilibrium with a partition of n intervals. Okay, now we have to, we can convert this into, remember ak and ak plus 1 can be expressed in terms of theta k like this. So we can do that substitution in this indifference condition. And then what we get is a difference equation, a second order difference equation, right? So it involves theta k minus 1, theta k, and theta k plus 1. And we can solve that difference equation to find the values of the cutoff points. Now it turns out that we can make the difference equation simpler. We can make it a first order difference equation by transforming the variable. So now let me get back to the slides. This is exactly the indifference condition as I said, right, with the values of the actions ak and ak plus 1 substituted in. But now, instead of writing down a condition relating the cutoff points, we can write down an equivalent condition involving the length of these intervals. Instead of the cutoff points, the length of these intervals. So let's define yk to be theta k plus 1 minus theta k. So this is the length of the kth interval in the partition we are trying to construct. Now you can easily check that if you rewrite this equation in terms of yk rather than theta k, you will get a first order difference equation which simply goes like this: yk plus 1 equals yk plus 4b. I'm not going to show you the algebra. I'll leave it to you to check that. It's very easy. You just do a little bit of manipulation and you go from this equation in terms of thetas to this equation in terms of y's. And now, as you can see, we have a very simple difference equation, first order, which basically says that each interval should be bigger than the interval to its left by the amount 4b, 4 times the bias. Okay, so these are our difference equations, and this overall constraint has to be satisfied too. All these intervals have to add up to the whole range of theta, which is of size 1. Okay, and this sort of thing is easy to solve. So when you solve it, you get this expression. Let me just help you along a little bit in terms of the solution. So here's our difference equation: yk plus 1 equals yk plus 4b. Okay. Now, we can express all of these intervals in terms of y1. So let's say the length of the first interval is y1. Okay, so first interval is y1. What is the length of the second interval? It's y1 plus 4b. What's the length of the third interval? It's y1 plus another 4b added to this, which is 8b. And so it goes. When we reach the nth interval, it is y1 plus this 4b term added n minus 1 times, right? So that means that the last interval is n minus 1 times 4b. Okay? Now, all the interval lengths have been expressed in terms of the length of the first interval, y1. So now we can add it all up. And if we add it all up, what do we get? We get n times y1 plus 4b times the sum of the first n minus 1 integers, right? So what is that? If you remember, the sum of the first n integers, the formula is n times n plus 1 divided by 2. So we have to apply it to n minus 1 instead of n. So that means it's n minus 1 times n divided by 2. Okay. So that's the sum of all these intervals. And we have this aggregate constraint that they have to add up to 1. So that's what we get. Okay. From this, we can solve for y1. So y1 equals 1 minus 2b n minus 1 divided by n. Okay, so that's our solution essentially. We have solved for the length of the first interval. And notice that this solution is a genuine solution because everything on the right hand side are parameters of the model, right? Well, b is the parameter and n is the number of intervals we are trying to create. Now, the only thing is, so that's our solution for y1, and yk just follows from that, right? We have to just add k minus 1 times 4b to get the value of yk. Now, the one concern is this a genuine solution? Does it make sense? For that to be true, this thing, what's in the numerator is less than 1. It's 1 minus something, and then we are dividing it by something larger than 1. So this is never going to exceed 1. So that concern is not there. But this may become negative. Okay? So for an n equilibrium to exist, what we need is the numerator in this solution is positive. It's non-negative. And remember that if the first interval is of positive length, then every subsequent interval according to our solution will also be of positive length because we are adding 4b to get the lengths of the other intervals that follow. So all we have to make sure is that the first interval is not of negative length. So what that requires is this numerator is positive, which means that b has to be less than 1 over 2n n minus 1. Okay, so that's our condition. So as long as the bias is not too large, in fact I can put a less than equal to, as long as the bias is not too large, specifically it's not larger than this, we will be able to construct a partition equilibrium with n. So that's what we have here. So let's sum up what we have found. So if you fix the value of b, the bias, then clearly there's a largest n that will permit us to construct an equilibrium of those many intervals. right? Because notice that as you increase n, the right-hand side is getting larger and larger. Its denominator is getting smaller, so the whole thing is getting larger. So if you fix the value of b, you will hit, and as you're increasing n, you will hit a point where this inequality is no longer satisfied. Okay? And notice that if this inequality is satisfied for some value of n, it will be satisfied for lower values of n. Right? So what that means is that for every bias, there's a largest integer, and you can construct these partition equilibria up to that integer value, but not anymore. So for example, for some bias, you may be able to construct at most 7 interval partitions, not 8. But if you are able to construct 7, you will be able to construct 6, 5, 4, 3, 2, and 1. 1 would be babbling. So n of b is the highest integer which satisfies this inequality, right? And that describes the most informative equilibrium in the Crawford-Sobel model. And notice that n has to be finite. As you take n towards infinity, no matter how small the bias is, eventually it will end up violating this inequality. Now, one thing to note is that, well, several things to note. If you look at this inequality closely, NB, the highest integer which satisfies this, is decreasing in the bias. So if the bias increases, the maximum n which will satisfy this cannot go down, right? At certain points it'll, as the bias increases, the maximum n cannot increase. It can only decrease. So NB is weakly decreasing in B. As the bias tends towards 0, the highest integer will approach infinity. It will still be a finite number, but it will become very, very large, because the limit of this as n goes towards towards infinity is also 0. And nb equal to 1. When is the highest number of intervals possible? Just 1, which means babbling, right? So nb equal to 1 means only babbling equilibrium is possible. And if you put n equal to 1 here, the right hand side becomes 1/4, and so so this inequality should have been reversed, right? So the nb equal to 1 if the bias is greater than 1/4. So let's step back and then think about what this means in plain language. So the general points are as follows. We are studying a model of cheap talk where there's conflict as well as common interest between the speaker and the listener, between the sender and the receiver. Yes? And the conflict is captured by B. So the higher is that bias factor B, greater is the conflict between them. Greater is the underlying disagreement about what action is optimal in a given state of the world. So when we have this sort of a situation, in equilibrium, speakers will not be able to convey fine information. The state of the world is a continuous variable. Theta is continuous, right? So in principle, the speaker can make fine distinctions in what the state of the world is. In equilibrium, because of credibility problems, the speaker will not be able to make these fine distinctions. However, there is scope for informative cheap talk, right? The receiver will learn something about the state of the world from what has been said, from the messages conveyed, but won't learn everything. So that means the receiver will learn coarse information, will receive information in broad categories, and fine distinctions and nuances will be lost due to credibility issues. So that's the sort of one important point. Then what we saw is that the bias or the degree of conflict between them. By the way, the term bias could itself be taken in a biased way, and I don't want you to take it that way. This is not to say that the receiver is a nice person and the sender is somebody manipulative. It's just that, bias just objectively means that the sender's preferences are different from the receiver's preferences. Yes? So there's bias in either direction. Relative to the receiver, the sender is biased. Relative to the sender, the receiver is biased. Right? So don't be misled by the term. So as the bias increases, there's further coarsening of equilibria. And this happens in two senses. First of all, as the bias increases in a step function sort of way, the maximum number of intervals that can be created gets lesser. Right? The most informative equilibrium will have fewer intervals or distinctions as we increase the bias. It doesn't happen in a continuous way, but as you keep increasing the bias, after certain points, the number of intervals goes down by a notch. Secondly, as the bias increases, even for a given number of intervals, the equilibrium becomes more right skewed. So the intervals towards the right become bigger and the intervals towards the left become smaller. Or the intervals become more uneven. Remember that our difference equation said that the intervals have to increase by the amount 4b towards the right. So when you increase the bias, you're making them more uneven. And as we saw in the beginning when we were studying the two-interval equilibrium, that has some welfare cost. In some well-defined sense, even for a given number of intervals, the equilibrium becomes less informative. The information which the decision maker learns is less useful. As the bias goes to zero, the most informative cheap talk outcome converges to full revelation. So essentially the limit, if you look at the most informative equilibrium and take bias towards the zero, the limiting partition is basically revealing the entire line. Okay? Only in the limit. There's some technical challenges in trying to prove that, and it has been proved in a paper by Spector, 2002. So if anybody's interested, I can give you the reference or you can look it up. Essentially, the loss of information in cheap talk that we are seeing is because of the bias. And if bias is very high, only babbling is possible. So two questions remain. One is equilibrium selection. Right? We have seen that you can construct a number of different equilibria, starting from babbling, n equal to 1, and then a number of different partition equilibria up to some highest integer. Yes? Now, which of these are more likely to be paid? Right? Any game which has multiple equilibria poses always this problem that which equilibrium is more likely? Can we say anything about that? So that's one issue, and the second issue is welfare, and we'll have a lot to say about welfare. But in terms of equilibrium selection, Crawford and Sobel in their paper make the case that the equilibrium with the highest value of n, highest possible value of n, is the one to look at. That seems more likely than the other equilibria. Now, it's not easy to apply standard refinements, equilibrium refinements like, the intuitive criterion of Cho and Krebs and other notions like that. If you apply them, you don't get a reduction in the number of equilibria. But there's a subsequent paper by Naveen Karthik and Joel Sobel and others where they come up with a novel equilibrium concept which shows that the most informative equilibrium, or the equilibrium with the largest number of intervals, is the one which will get selected. The others drop out if you apply that criterion. In any case, in general, we'll often look at the most informative equilibrium. Now, the other issue is welfare. So that's the thing that I'm going to turn to next.